All right, so in the last lecture, we finished up, we've just sort of started talking about quarks. And in the last lecture, we finished up discussing the Yukawa interactions between the Higgs and the different quark flavors. And we saw that the quarks are sort of very much in the Standard Model very different from the leptons, in the sense that in the lepton sector, there's no equivalent of the right-handed up quark, and this means that one cannot simultaneously diagonalize all of the quark Yukawas in the same way that in the lepton sector, because in the absence of right-handed neutrinos, you only have one Yukawa, so you have the freedom to diagonalize it. We'll come back to that perhaps at the end of this lecture series, although we may not have time. And so this meant that, so first of all, yesterday we discussed the up quark sector, and we chose the freedom. It's a basis dependent thing, but we can choose to diagonalize the up quark Yukawas. So that's what we did. We diagonalized the up quark Yukawas. And then we studied their Yukawa couplings and then their mass matrix, which is a consequence of that. And we saw that everything is sort of fairly vanilla, sort of as you'd expect, with the exception of the top quark, who has such a large Yukawa coupling in natural units, it's of order 1. And because of that, it has a profound influence on the Higgs sector of the Standard Model. We saw that typically loop corrections in the top sector will be pretty big. The sort of effective Yukawa fine structure constant, especially when you include the number of quark colors and things like this, is actually a pretty big number. You know, 4 pi is 12, and so this is 6 over 12 squared. Sorry, so that's 4 pi. So that should be 6 over 4 pi. So this is sort of like a half, which is a pretty big number in terms of fine structure constants. And this fed through all the way into things like the production of the Higgs boson, which is at a hadron collider is dominantly through a loop of top quarks, and also fed all the way into the decay of the Higgs boson, which is not predominantly into photons, but the cleanest channel for the Higgs boson decays to observe at the LHC is actually the decays into photons. That was actually the driving channel that led to the discovery of the Higgs. And there's also a contribution involving the W quarks as well, but the one involving the tops is important. And so we saw that the tops are very, very important for Higgs physics, even though the Higgs cannot decay into them, and that's a direct consequence of the fact that the top Yukawa is so large. I should also point out that, you know, the Higgs sector is very special at hadron colliders. It's a different story at lepton colliders, but at hadron colliders, because you're colliding big balls of gluons and quarks, everything is the dominant production is really going through loops. So it's really going through a quantum mechanical effect, which is sort of intriguing. You know, this is not naively, if you could collide anything you wanted, this is not naively the thing that you would think to shoot for, is to go through a loop effect to produce the Higgs boson, but in fact, that is the case. And actually, that sort of those questions were actually fleshed out here at CERN, in the CERN theory group in the 70s by people like Mary Gaillard and John Ellis and co. And furthermore, what's sort of really intriguing is that this branching ratio into photons is super, super small. It's by far subdominant compared to the other branching ratios. It's not the most subdominant one, because you can always go to some very rare decay and call that, you know, that's more subdominant, but it is very subdominant. But because it's such a clean channel experimentally, photons are very clean final state particles in a particle detector. That is actually what drove the discovery of the Higgs. So it's very, I think, counterintuitive. Higgs physics at a hadron collider, the sort of the dumb obvious thing is not the thing that leads to physics. Sorry, there it goes. So that was yesterday. Now we want to go on and discuss the down quarks. And there the story is very different, because in this basis that we've chosen, we cannot diagonalize this down quark Qcd. There's always, as we've discussed now a number of times, there's this unitary matrix in here known as the Ckm matrix. And this Ckm matrix will have profound implications for the physics of down quarks. So let's see how that goes. So let's write down now, we'll leave this here because we can refer back to it. And we'll start by considering the down quark mass matrix in this basis. All right, that's not come entirely off, we'll have to live with it. Okay, so what is the down quark mass matrix in this basis? So we've got this epsilon thing here, which basically means that Higgs dagger dot epsilon becomes that's been dot q, or just dot q, becomes 1 over root 2, and then we have a row vector v plus h, and then 0 dot q. And if you recall, q was d let's call it L, for instance, and UL. I can't remember what we called it yesterday. Yeah, that's what we called it yesterday. Okay. And so then the mass matrix in terms of DL and DC, which are the left and right-handed components of the down quark, the mass matrix for the down quarks is now Mij. D is V over root 2, where V is the vacuum expectation value of the Higgs. That's, once the Higgs is rolled out to that minimum down at the bottom of the Mexican hat potential. And then we have VCKM, and then we have lambda B, lambda S, and lambda D. And this matrix here is diagonal. But the whole mass matrix is not, because of this VCKM. And where does this come from? This is in flavor space, these IJ. So this is really coming from a Lagrangian that is looking like, in terms of these, the bottom strange and down quark, something like V plus H over root 2. And they have BL, SL, DL, VCKM. Then this diagonal matrix, lambda B, lambda S, lambda D. And then over here you have BC, the right-handed guys, SC, and DC. These are all zeros. Okay, so that's where it's come from. However, to work with the mass eigenstates, so we will need to perform one last rotation, which is actually a rotation of the left-handed down quarks. So if we look at this representation of Q here, before, when we did the rotations to diagonalize this term here, we were doing a rotation that was SU2 invariant. It was treating both components of Q in exactly the same way. So Q has the down quarks and the up quarks in it, both of the left-hand type. And for each generation of up and down quark, whether it's the third, second, or first generation, we were performing this rotation in exactly the same way. So it was an SU2 preserving rotation. And it was because of that SU2 symmetry that we were unable to diagonalize this thing at exactly the same time. However, the mass matrix, what are the masses of the fermions? The mass, I mean, there are many ways of describing it, but for me, the mass is essentially if there were a pole in a scattering amplitude, that corresponds to an internal, the mass of an internal particle. So it's the position of a resonance, for instance, which also applies for fermions. And so the mass of the bottom quark, for instance, cannot have this off-diagonal matrix in it. So the actual mass matrix itself needs to be diagonalized. But now that means we need to do a rotation on the left-handed down fields, which is different from the rotation that we did already on the whole of Q, so including the left-handed up fermions. So what we know, so this rotation that we need to do will be of the form, B, L, S, L, D, L, goes to V, dagger, Ckm, B, L, S, L, D, L. And this will bring this mass matrix to a diagonal form, which is great. However, as I've repeatedly said, this is treating the down type left-handed quarks differently from the up type left-handed quarks. And this is going to have consequences because this rotation is not something that respects SU2. It's okay because SU2 has been spontaneously broken. So we expect to have consequences because of that breaking of SU2. If SU2 remained a good symmetry and the Higgs did not get a vacuum expectation value, this is as far as you could have gone. There would be no quark masses whatsoever. But SU2 has been spontaneously broken. And so the consequences of that will actually be quite profound. So I'm going to rub off this side of the board here. And we will study again what the kinetic terms were. So the kinetic terms were like IQ dagger D/Q equals I'm going to write this all out in component form. It's going to be a real mess, but bear with me. D dagger L U L dagger, so that's the Q. And then we are summing over the D/, if you recall. In standard notation, the D/ means we've summed over, if it were Dirac fermions, we'd be summing over D mu or big D mu and the Dirac gamma matrices. We're working with Weyl spinors here, so it's actually the Pauli matrices that we sum over. So we have D dagger L, U dagger L, and then we summing over sigma mu. And then the covariant derivative itself. And you have to be careful with how to space things here. DL, UL, and we'll have D mu, which will be multiplying the identity matrix as usual. In SU2 space, it's the 2x2 identity matrix. And then I, and these guys have hypercharge of 1/2, so I'll get I over 12 G prime B mu times the identity matrix. And last but not least, the electroweak bit, the SU2 bits, we get IG over 2. And then the matrix that you've seen now quite a number of times, W3 mu minus W3 mu, 2W plus mu, 2W minus mu. And there's a gap between these. These are the 4 components. And then plus summation conjugate. Okay. So now let's consider what happens when we do this rotation just on the down component of this 2x2 matrix. So when we do it, of course, the bits that the bits, this is a big matrix, and let's just write it in red. Let's write it like this. So the bits in here, in the 2,2 component, concern only UL dagger and UL, and we're not doing a rotation on that. That's already all been diagonalized by the rotation we did on the whole SU2 doublet. So nothing changes there. Similarly, the bits in here will remain unchanged because in the 1,1 component, we've got DL dagger and DL, both with all 3 flavors. But DL dagger DL, when we rotate that by a unitary rotation in the center, we'll get U dagger U, or VCKM dagger VCKM, CKM, and so we just get the identity back. So that remains unchanged. So the only bits that we modified, only parts that we modified will be the parts in these two components, in here and in here. In other words, the off-diagonal pieces. Super. So we can just study them. Let's forget about the rest of the pieces because we know that they will remain diagonal. They will be the sum over now the mass eigenstates in here and here, but these two off-diagonal pieces will be changed. Okay. So what will they look like? I'll maybe stick with red for this. Oh, sorry. Then the off-diagonal bits will give us the following terms. Minus G DL dagger VCKM W slash plus, for instance, UL plus Hermitian conjugate. So we see that in the mass eigenstate basis, the interactions with the charge current with the W bosons alone are now become off diagonal between generations if VCKM is not proportional to the identity matrix, or is not the identity matrix. And so this is a big deal. The charge current interactions are not diagonal, and what that means is that you can have interactions that have various forms. For instance, one of the types of interactions would be a strange quark and U quark. But you notice it's always changing charge, so it goes between up and down sectors, not between down to down or up to up, something like that. We can have interactions that go between generations, but only involve a change of charge. And so we get Feynman diagrams, we get interactions that would have, the normal G in here. But also some, CKM element, let's say the SU element, maybe a dagger in there, I'm never quite sure. And for instance, a W plus coming this way and this way. So we call this flavor changing. Changing charge current CC interactions. And no flavor changing neutral current interactions. I put in brackets at tree level. This second piece, you'll often see things like no FCNCs, flavor changing neutral currents. So no FCNCs, and that's related to a mechanism known as the Ckm mechanism. I'm not sure who the G might be Galasio, Iliopoulos, Muscava or something, GIM, not JIM like we would spell Jim. And this is a really good rule of thumb because it means that, so I'll come back to two topics. First of all, the flavor changing charge current interactions have absolutely profound influences. So they relate to, for example, things like kaon decay. So kaon decays into pions can proceed via these sorts of interactions. Similarly, there's mixing between, for example, a W, and you could have that's not flavor changing, but a DNU. Sorry, forget that, that's not flavor changing, it's besides the point. But so we can have flavor changing charge current interactions. But this fact that at least at tree level we don't get any flavor-changing neutral current interactions means that if you have imagine you are trying to solve some other problem, or a theorist colleague is trying to solve some other problem, they come up with some theory beyond the standard model to try and address that problem. It might be that there's an anomaly in flavor physics and they want to build a model to explain it. Or it might be that they want to solve the hierarchy problem, which is something you will have heard of and we will hopefully discuss in the last lecture. And there, in that model, there might be some flavor structure. Now, generically speaking, if you were to write down any old theory, it's quite likely that you could introduce tree-level flavor-changing neutral currents. But the fact that the standard model does not have tree-level flavor-changing neutral currents then becomes a very powerful fact, because it means that if you look for evidence of flavor-changing neutral currents, so things that are preserving charge, then you can actually be extremely sensitive to theories beyond the standard model. And so many powerful constraints on theories beyond the standard model, even if the new particles that are being hypothesized are quite heavy, you know, maybe they're in the multi-TeV regime, quite a lot of important constraints come from looking for flavor-changing neutral currents, because the standard model has this extra protection built into it, just because of the structures, because of the charge assignments and so on. This extra protection comes along for the ride. Okay, there's some other things I want to just mention briefly before going on to discuss gluons. And the most important one concerns VCKM in here. So as you recall, I emphasized that a general unitary matrix has 8 free parameters. There's the entire family of unitary 3x3 matrices requires 8 parameters to map the full space of possible matrices like that. However, we could always perform rephasing of the quark fields to get rid of some of the phases and some of those parameters, essentially 5 of them. Oh no, sorry, 4 of them. And so what's left in the Ckm matrix is effectively 3 rotation angles, and I said this a few times, and a phase, a complex phase. And when we were discussing CP, I gave a sort of a relatively basic argument as to why that phase corresponds to CP violation. We did a CP transformation on the standard model Lagrangian, that the phase in here is non-zero, then the Lagrangian is not invariant, which means then that parameter is related to CP violation. So that CP violation should show up somewhere. If that phase is non-zero, then in all of this mess or beautiful mess, that phase is going to feed through somewhere into some measurement that one can perform. And in practice, it does. In practice, it does show up in physical measurements, and this is what led to the discovery of CP violation in nature. Now, there's a variety of different measurements one could make these days that are sensitive to that. But where it really showed up most profoundly was in kaon physics, so literally relating to this these sorts of vertices between strange quarks and, for instance, up quarks. And how it was discovered was quite surprising. It may not have been a surprise, but I probably would have been surprised. Because what happens is that one can form kaons out of things like strange quarks and up quarks. So that would be a charged kaon, the kaon mesons. And this is sort of the anti-quark and quark. That's why anti, there's a little backwards arrow there, which means anti. You can put a bar across the top if you wish. And so the anti-quarks and quarks can form mesons that don't carry baryon number, but can carry flavor quantum numbers. And so they're charged and they're K pluses and K minuses, but there are also neutral pions. And one can form these neutral pions out of strange quarks and down quarks. And there are different mass eigenstates of these pions. There are different linear combinations you can form. one that is CP even and one that is CP odd. And the CP odd one is very long-lived and the CP even one is very short-lived. And the reason for that is that the CP even one can easily decay into two pions. For instance, you have a neutral kaon decays into two pions. And a pion has CP odd. So two pions together is CP even. So a CP even thing can easily go to two CP odd things and conserve CP. Sorry for saying CP so much. And so there was the long-lived guy that was believed to be a CP odd particle, and it made sense that it was long-lived then because it was CP odd. So it had to decay to something that was CP even and CP odd, because two CP odd things, at least at zero angular momentum, two CP odd things would not suffice. And yet it was discovered after lots and lots of kaon measurements that the long-lived kaon, the k-long, which was believed to be exactly CP odd, could decay after some time into a pair of neutral pions, which this decay then violates CP. So what it means is that the mass eigenstate itself could not be an exact CP eigenstate. And the only way for that to occur would be if the CP phase in this 2x2 matrix was non-zero. And that's essentially how CP violation was observed in nature. But it's a big deal, right? Because CPT is a symmetry. So if you violate CP, you violate T. So it means that you have some non-time reversal symmetry. If you run things forward, you don't get necessarily the same result as if you run a simulation forward, you don't get the same result as if you run the simulation back if you have T violation. Now that's very interesting in its own right, but it could even have consequences related to, for example, the generation of the matter-antimatter asymmetry in nature, because that's one of the three conditions required for generating a matter-antimatter asymmetry is that. Well, I'll tell you the three conditions quickly, and then we will hopefully get back to it, but this is a good place to point it out. You have to have some out of equilibrium physics happening, so not everyone in everything in thermal equilibrium. You have to have some baryon number violation somewhere, because if you're going to create more protons than antiprotons, there must be some violation of proton number, baryon number. And the last thing is you need to have some sort of physics that's not time reversal invariant. Time reversal symmetric, sorry. And CP violation does that for you. And it just so happens that the CP violation in the Ckm matrix could have helped with that process. Sadly, though, it's not quite enough, and those other ingredients don't quite work out in the standard model, but there could be potential connections there. Okay, so that's all I want to say about the quarks themselves. Now I want to go on to QCD and actually sort of tidy up some aspects from the previous lectures that I was not super clear about. I sort of swept a couple of things under the rug. The astute amongst you will have noticed this. The less astute, maybe not. But nonetheless, I will pay for my sins and spell everything out in more detail now. So I want to talk a little bit about QCD and a little bit about the gluons. And again, some of the sort of conceptual aspects. I will go on yet another rant at the end of this lecture about a conceptual aspect relating to QCD, which I think is very, very important to be aware of. Okay, so QCD, quantum chromodynamics. So if you recall, the interaction between quarks and gluons, again, comes from the kinetic terms. So we have something like I, Q, dagger, D/Q, plus then, the ups and the right-handed ups, right-handed downs. D/ was, d mu, sigma mu. And so d mu, until now, we've actually only really been writing in the electroweak parts of d mu. We've not really been writing in the whole story. So we have the d mu, we've electroweak stuff that we've studied to death. And then there's G strong. I'll call it big G, A, mu, T, A. Where this is the gluon, because this is a gauge symmetry, so the gluons the gauge fields of QCD have to enter into the kinetic terms, and these are the generators of the symmetry. So these are specified. We'll come back to them in a second. So we put this in here, and we see that there are interactions as well between quarks of different color and the gluons, which look like this in terms of Feynman diagrams. We like to give, for reasons I've never really fully understood, swirly lines for gluons. And there's a GS in here, and then a generator matrix, Tij. We've got G and mu, Q, I, Q, J, dagger. Okay, so we also have to include, when we have quarks, we have Feynman diagram interactions that give you Feynman diagrams like this. The strength of the interaction is G strong, and you have to recall that there's one of these generator matrices in here. Now let's, so that's fairly straightforward. Actually, it's the same. So for the anti, for the right-handed guys, we get the same thing, but we're just with the opposite sign. But when we get to the gluons, we'll get to the part that I have glossed over, which is related to the field strengths for the gluons. So we only really ever discussed in the previous lectures the field strength tensor for an abelian gauge theory, and I showed you that this thing F mu nu, which is equal to d mu a nu minus a nu d minus d nu a mu, was invariant under the gauge transformations, but I actually only did that for abelian gauge transformations. And it turns out there's a procedure if we want to construct a gauge invariant field strength, which is actually much simpler than just staring at it and trying to construct something by hand. And that's to use the commutator of these covariant derivatives. So we can write that F mu nu is 1 over Ig d mu d nu, the commutator of these covariant derivatives, just using the covariant derivatives as they act, for instance, on a fundamental representation like these fermions here. And you can see already, if this were electromagnetism, for instance, and this were E, then this would give us exactly what we wanted, because we would get d mu a nu minus d mu a mu. And that would be the end of the story, because the covariant derivative, everything in here commutes. So you get also a d mu minus d mu, but derivatives commute, so that term cancels, that's the same thing. And you would get this, but with something like an identity matrix, which commutes and then cancels, and that would be it. So that's one way that we could have constructed our covariant, our field strength tensor. But when it gets to non-abelian gauge theories, it's a little bit more involved. So we can write this in. So this would be 1 over Ig, something like d mu plus Iga. Oh, I should be using G's, not big G's, sorry. Big G A mu Ta, and then d nu plus Ig, big G, I'm going to make this mistake a lot, big G B nu Tb, and then minus this, the same thing, but where you swap mu and mu, like that. Okay, now a bunch of terms cancel, so the D's, the two D's, that commute, so you get the same thing in here with the minus sign, it cancels. But these bits will also cancel, because you can swap the labeling of A and B, and so the bit multiplying this will give you the same thing, practically speaking, as in here, just with a swap of indices, and that will cancel. But the bits that don't cancel will give us the following terms. We will get what we expect is, we'll get the usual thing, d mu G, I better be very careful with G nu B Tb minus d nu G B mu TB, and then plus IgA mu A B nu sorry, I was talking nonsense there. No, this doesn't cancel. What we get when we get this times this, we'll get this thing here. Then I'm about to write down. And then the commutator, that was just totally wrong. TATB. Okay. So I can simplify this. I can pull out this, and I'm going to do a little bit of relabeling of the indices. It doesn't actually change anything, but see, I've got BB here. I could call that CC or whatever I wanted, KK. Same here, and I can do a bit of relabeling of indices in here to write this in the following way, which is D mu A mu. I'm so sorry about these A's and G's. This should be a G up here. A G here. G. G C nu minus D nu G mu C plus I little g, the gauge coupling, G nu A, G nu B, and then something that we would call a structure constant, FABC times TC. And this is the structure constant, basically TA, the commutator of TATB is the structure constant FABC times TC. And it's unique to the symmetry. So for instance, I think we're okay for time. For instance, for an SU2 symmetry, we're doing SU3 at the minute, but for an SU2, this structure constant is just the antisymmetric tensor epsilon ijk, which you may know. And you can find that by doing the commutator of the generators of the SU2 group, which is just the Pauli matrices with some normalization constant. I think there's an I over 2 as well. I should point out that the generators for SU3, these T matrices, there are many different bases. You could write them in many different ways, but if you want to look up an explicit representation of them and derive even what the structure constant is, you should search for the Gell-Mann matrices. These are known as the Gell-Mann matrices. Okay, so finally using this, I can't believe I said that these things cancel. I'm very embarrassed about that. Finally using this, we can construct now an SU3 invariant field strength tensor, and using that we can construct an SU3 invariant Lagrangian. So we construct this SU3 invariant Lagrangian. It looks like this: -1/4 times the trace. So we can trace now over this guy. So this thing here is this thing here, and you see the only sort of matrix part of it is multiplied out the front here. And so if we trace over this times itself, we'll get the trace over these things, and then TC multiplying some other thing, let's call it TD, the same set of matrices. And the trace over Gell-Mann matrices, and in general these generators for an SUN group, will just give you the identity matrix, sometimes normalized with an extra factor of 1/2 or something like this. So we can take the trace, F mu nu, F mu nu. And this finally gives us that the kinetic terms for the gauge fields look like this. So it's a sum over A, and then we've got this thing squared, D mu G A nu minus D nu G A mu plus I G F A B C G B mu G C nu, all squared. Okay. So now we get gluon interactions as well, because you see that these bits, this bit squared is just the normal thing that we recall from the U1 gauge theory, but this thing isn't U1, and because the generators did not commute, we have these extra terms here, and you can see that when you square it, you get things like this bit squared, which will give you 4 gluons in the interaction. You get things like this cross term between here and here, which would give you a 3 gluon interaction. And just to give you a taste of it, I've probably made normalization errors here, but to give you a taste of it, you get things like a 3-gluon interaction, which looks like this. You have G, F, A, B, C, something like this is a G, B, mu, G, mu, C, and G, A, gamma, where the momentum in here is K. Then you get something like G, F, A, B, C, G, mu, gamma, K, mu, minus G, mu, gamma, K, mu. And then you have to sum over permutations. That's come from the cross term here and here. And similarly, from this thing squared, we'll get interactions that look like this. G, C, mu, G, B, mu. So it's A, mu, B, mu, G, delta, let's call it, D, G, going to E now, for E gamma, and then you get something like F, A, B, C, F, C, D, E, G, mu, gamma, G, or this is, sorry, let's call it eta. Let's call these things eta. These are just the Minkowski metric. Eta, mu, and eta, mu, delta, and then you sum again over permutations. Okay, perfect. So we've got about 7 minutes left. So we see that gauge invariance in forces, and this is in a particular gauge. I'm working in a specific gauge here. I've not added the terms that one would have for a general gauge. You can look that up. It's called the Feynman-Psi gauges. But in this particular gauge, you can see that gauge interactions are completely fixed, the form of gluon self-interactions. I should say, one should take care to note that, for instance, this trilinear vertex, sometimes people refer to it as gluon self-interactions. So gluons interact with gluons, but they never actually interact with themselves. If you could tell color index apart, now this is a bit of a slippery slope to go down discussing, but if you could tell color index apart, then you'll see that no 3 same gluons ever interact with another, because FABC is antisymmetric, because it comes from the commutator. So you can have there's no FAAA, that's 0. So no 3 alike gluons ever interact. And that's one of the reasons that the Higgs self-interactions are so exciting to go and look for, because the Higgs is really the only particle in nature that can have a 3-point, in the standard model, sorry, that can have a 3-point interaction with itself. And that's because it has flouted any respect for gauge invariance whatsoever, whereas by breaking SU2 symmetry, whereas the gluons do not have that freedom, so they don't really actually interact with themselves. So these interactions are very, very important. For example, in collider physics, you can collide 2 protons, and you can have a hard interaction between a gluon in each of the protons that then creates 2 gluons, which give you 2 jets. So these are very, very important interactions. But I think conceptually, the real big hitter in terms of these gluon self-interactions relates to a property known as asymptotic freedom. Now, this was something that was discovered by Gross and Wilczek and Politzer in the 70s. I believe it was Wilczek's first paper, and I believe with Gross, and I believe it was Politzer was doing his PhD as well. So they were fairly young, and Gross was a young faculty member. And I think it's profound. It's very, very deep. So I'm going to try and quickly sketch what asymptotic freedom is about. Okay, so if you recall, in a quantum field theory, there are some unfixed parameters. Now, there's some folks might worry lots about infinities and renormalization, blah, blah, blah. But ultimately, the theory cannot self-predict the values of those parameters. They just have to be measured. And so what you do is you measure, maybe not necessarily the bare parameter in the Lagrangian, but you measure some scattering process, for instance, for a coupling, or the position of some pole in some scattering amplitude that gives you the mass. You can look up, for instance, the Z pole plots from the lab collider, which are very beautiful. And so these three parameters, ultimately, you have to make a measurement that fixes them. There is no way that the theory will self-explain to you what value those parameters should take. And so the same is true for QCD. Now, there's only one gauge coupling in QCD. There's not charges like in QED or with hypercharge. And that's because it's non-abelian, so there's no notion that corresponds in any way to what we would normally conceive of as being charge in that sense, as a sort of free parameter that one can select. And so we must perform a measurement, and we can do it with one measurement to fix the strong CP, sorry, the QCD gauge charge. One way you could do it is to, for instance, scatter quarks through gluon exchange, and there's a G in here and a G in here. It's quarks Q bar, for instance, QQ bar, at some energy scale mu. Okay, and from that scattering process at some collider, you can extract the value of the strong coupling constant. Okay, then one can ask the question, well, what if I were to perform exactly the same measurement with exactly the same apparatus and everything, just at a different energy? If I were to do that, then given I've extracted some value at this energy, let's call it mu, then what would it be if I did the same thing and I extracted the gauge coupling in the same procedure at a different energy? How would that gauge coupling, what would the value be in relation to the one that we've extracted at a different energy? And it turns out that classically speaking, if there were no H bar in the game, it'd be the same. It's just a fixed parameter. So you'd extract exactly the same gauge coupling. But quantum mechanically, that's not the case. Quantum mechanically, there are effects. It's terrible writing. That correspond in terms of Feynman diagrams to loop diagrams, things like this. You have a gluon vertex with two quarks, and then you could correct that. Have a one-loop correction, for example, involving gluon exchange. You can have the wave, what we call the wave function normalization. So you have the two-point function of the quarks. The propagator can be corrected with diagrams involving gluons like this. And even the gluons themselves can have diagrams that correct the gluon propagators involving gluons. So you see everywhere here there's a G strong, G strong, G strong, and so on. And the result is that the gauge coupling changes. So if you were to measure it at different energies in the same way, the value of the coupling that you would extract would depend on the energy. So if you fix it at some energy scale and that's done, you've done the fixing. So now you can predict everything. And then if you were to go and measure at a different energy scale and relate it to the one that you extracted at some different energy scale, it will not be the same. And we call this running, and it's related to renormalization. And it's a fundamental property of nature. It's not something that's negotiable. And some folks worry about infinities in quantum field theory. I don't believe that is I believe that it's unfounded to worry about it. But the presence of infinities in quantum field theory are actually directly related to the existence of running. Anywhere you see a logarithmic divergence in some quantity that you may calculate. So for instance, if you were to do these calculations at one loop, you'll see a whole load of logarithmic divergences. Well, they are intimately related. Those divergences are intimately related to the fact that coupling parameters have to run in nature in quantum mechanics. They have to change and evolve with energy scale. And if you can calculate what the magnitude of this effect is for QCD, and what it tells you is that the rate of change of, for example, the strong fine structure constant, let's call it alpha s, this is gs squared over 4 pi, with respect to the log of the scale that's changing, so d alpha s by d log mu, which is just d alpha s by d mu all multiplied by mu to make it dimensionless. Goes like alpha s squared over pi times minus 11 over 6. You can just calculate it from all these diagrams, nc, plus nf over 3. So nc is the number of colors. So for QCD, this is 3. And nf is the number of flavors of quarks, essentially. And the most important thing, take-home message from this, is that the sign of this is different from the sign of this. So if nf isn't too big, let's calculate. If nf is less than 11 over 2 nc, then the sign of this whole thing is negative, which means that if we were to plot, in this instance, if we were to plot the strong coupling constant against the scale, it will actually, if you measure it at some scale to take this value, then as you go to higher energies, it will become smaller. Logarithmically become smaller. Or not. So it turns out if you do the same calculation, for example, for hypercharge, there's no factor like this because there's no gauge boson self-interactions. And you just have this and it's positive, which means that hypercharge, if you just have fermions, is going to get bigger. The gauge coupling is going to get bigger and bigger as you go to higher energies. And equivalently shorter distance scales. Okay, so this is all a little bit pragmatic or prosaic, the way I'm presenting it. But why do I say that this is so profound? It's very profound because normally quantum field theories have what we call is a cutoff, a point at which they sort of become self-inconsistent and they have to be replaced by some more fundamental microscopic story. So the obvious example of this, and there's many there, it's all over the history of physics, but one obvious example is the theory of pions and baryons and things like this, the effective theory of QCD below the QCD scale. If you had only ever measured physics at that energy scale, you'd never built another collider above that energy scale, so you just had only ever played with pions, you would know that that theory has to become inconsistent at around a GeV, because you could look at the properties of the interactions and so on, you'd see that it becomes self-inconsistent, scattering amplitudes become larger than one, you start to, at some energies, you'll be predicting probabilities that become larger than one and things like this. We call that unitarity violation. And so you know that it has to be replaced by something else. And indeed, the standard model, for a number of reasons, has exactly the same properties. And this is also not something that's restricted to particle physics. It happens all the time in condensed matter physics. The Landau-Ginzburg theory of superconductivity is an excellent example. The microscopic story is the BCS theory of superconductivity, which explains sort of really why the microscopic physics about what's happening. So that's the UV completion, we call it. Other examples include basic inconsistencies between symmetries. Newton's theory and of gravity and special relativity could not be consistent. So even though at long distance scales, Newton's theory works very, very well, it's not UV, it needed a UV completion to make it consistent with special relativity. And so if you're working at relativistic energies, you have to really use general relativity. Nonetheless, Newton's theory is a good low energy approximation. That's another example. Many, many examples of this. Yet, if we look at hypercharge, the same thing happens. So if we have hypercharge, the gauge coupling grows up and up and up and up. Now, you may not care because maybe there's gravitational physics that should have kicked in by some scale, but nonetheless, it cannot be, the hypercharge sector of the standard model cannot be UV complete in the sense that there must be some more fundamental microscopic theory that you would hit if you had a theory of that nature. But QCD is different. QCD, if you just had QCD on its own, so not hypercharge, electroweak interactions, and forget about gravity. So this is in a hypothetical sort of theory space, and you just had QCD on its own, it never breaks down. It is a perfectly acceptable UV complete theory because as you go to higher and higher energies, the gauge coupling is getting smaller and smaller. It becomes more and more perturbative, because the gauge coupling is smaller, perturbative calculations like these loop diagrams and so on just behave even better and even better. And ultimately, when you go to arbitrarily high energies, even though that's not a realistic scenario, the gauge coupling ultimately goes to 0. And so QCD in and of itself, or theories like QCD, can be UV complete, which is a whole different beast. And it means that you can calculate all sorts of things that you wouldn't necessarily be able to calculate. It means that also your quantum field theory is on a very firm footing, because you know that as you go to smaller and smaller distance scales with some microscope and you're probing in, that actually nothing's going to go wrong. What implication does that have for nature? I'm not really sure. You know, for the standard model, hypercharge is badly behaved, so we don't have that positive aspect. Although you could hope that hypercharge and the electroweak theory and QCD could be embedded into some larger theory which is UV complete and does have asymptotic freedom, and that's something that people study. Perhaps even gravity itself could have this sort of behavior, and we haven't quite figured out how to make that manifest in the equations. But nonetheless, it's a very important and interesting conceptual aspect of QCD, which I think is worth having my second rant about. Okay, and I will finish there for today. And in the last two lectures, we'll talk more about QCD at low energies, and then some aspects of physics beyond the standard models. We try to guess about what's going on at shorter and shorter distance scales.